Hi class, welcome to Grad Stats, our Lab 2 in RStudio. Our goals for Lab 2 are to work with correlation, simple regression, and multiple regression. And part of that is just building this statistical toolbox and being able to evaluate simple and multiple regression from the point of checking those first assumptions that you want to look at when you are running a regression. We are checking out the research question of, are personality factors significant predictors of students' perceptions of research methods? And our hypothesis would be that we expect conscientiousness and cognitive ability to be predictive of students' perceptions of research methods. The study variables themselves are the big 5 personality traits and cognitive ability to look at are those predictive of perceptions. So our tasks, we want to look at correlations, and correlation is the basis of regression. So while we are gathering descriptives about the continuous variables, we're also looking at how the study variables are related to each other and communicating that to the reader. We also need to evaluate the assumptions of regression, specifically normality and bivariate linearity, so that we then conduct 2 simple bivariate regressions, and simple just means one predictor, one outcome. It doesn't mean it's easy, it just means it's 1-1. And a multiple regression, so 2 predictors with 1 outcome. And then looking to interpret the results and gather the relevant information needed to communicate findings. To prepare, you need to download the dataset called RMI version 2 DAT, and you'll want to work with the starter tables to build your correlation table. And the packages we're using in this Lab 2 are Tidyverse, Core, H Miscellaneous, MBES, and LM Beta. I'm going to start by loading Tidyverse. Alrighty. Now reading and data, this time we're going to load a tab delimited data set. And tab delimited is helpful when you might have commas in the data itself. Like if I had a variable that was city and state, like a variable called location, and the city-state data within that case for that variable was Pensacola, Florida. If I try to upload that or import it as a comma separated values, that comma is going to make the program think that those are 2 separate variables. So location and this other one, whatever the next variable after location was. And it ends up moving your data over and creating weird variables that don't mean anything at the end because it pushed information down across the variables. It misaligns your data set. So if you have a tab delimited file, you want to make sure that you're importing it as a tab delimited. So we'll do that. And this time we are going to use the import dataset wizard. So we're going to come down to from text reader and then navigate to where you put the file, typically your working directory. Oops, wrong. Oh no, I managed to pick up the right one. That's good. Okay, here we go. So this is RMI _ V2 DAT. Notice how when it first comes in, they're just all squished together. All the data is squished together here as a character type of measurement. And that's definitely not what we want. So we need to let it know down here in delimiter, the reason it's doing that is because it's on this delimiter comma. So I'm going to change that to tab, give it a chance to catch up to me here. And now it's spread it out. You see how that looks more like a data set instead of what it came in at the beginning? We're going to change case ID to character here so that we don't have to do it in the code later. Normally, we would set our categorical variables to factor here, but we're not working with them at all for Lab 2, so I'm just going to leave them as they are. I am going to change the name here to Lab 2, and you can do that during import so that you're not typing out some really long data set name if that's, how it came in. And you can even see how the code is being written to import that data. So it's like a little helper wizard, just like SPSS does. So we will import this. And let's take a look. Okay, we have 79 observations of 17 variables. That's good. And let's take a look at it using summary. We can see all the variables here that they all came in as numerical except for class ID. Good. Now we're only going to examine the variables of interest, the study variables. So let's make a smaller subset of only those variables. So the case ID, and then the personality traits, cognibility, and the outcome of perceptions of research methods at time 2. So now we have 79 observations of 8 variables. Now we're going to use those skills we have been working on to describe the variables. And because they're all continuous, we can just describe the continuous variables. And this says, make a new item called Descript in the environment. It's assigned by the Dataset Lab 2.1. Then summarize if the variable is numeric, so that's my function and my arguments. List the mean and standard deviation and ignore if there's a missing value. So now I have Descript and all of my means and standard deviations here in the environment, or I can click it and have it come up in the script window as well. Now, there's another way to do pretty much the same thing. I can use my piping tool and say, give me an item called Descript2 using Lab 2.1. Then summarize, and I'm giving it an order. I'm saying, give me the mean, and I gave it a name, and give me the standard deviation for openness, and then the mean and the standard deviation for conscientiousness, and then the mean and the standard deviation for extroversion. So I kind of gave it each at a time and show you what that looks like. Looks kind of the same there, but if I click it up here on the side, now I have them right beside each other. The mean and the standard dev, the mean and the standard dev. Whereas before it was all the means and then all the standard devs. So it kind of depends on what you feel more comfortable getting into your table. All right. So we have the mean and standard deviation, but we also want the correlations, the relationships between all the study variables. And we can also use our pipe operator and select to just get the continuous variables so that those are the only ones we're looking at. So I'm taking off case ID there is what's really going on. So and I just gave it that name, lab2.continuous. It didn't have to be that. And then I can run the correlate function from the library core on that whole thing, that lab2.continuous, since it doesn't have anything but continuous variables in it. When I do that, down here in the console, I have the whole correlation table. You have that diagonal where it's just like openness to openness. And here they don't put ones, they put NAs. But all of this information in the lower triangle is the same as the information in the upper triangle. And the red numbers are just because they're negative. It's not, we don't have p-values here, which could be problematic because we need to know the p-values. But it does give us the information quickly like that. So we can keep this in the environment by just giving it a new name and running that same command that was up higher with the new name here. And now we have it as something we can see a little prettier even in the script window, the script panel. Still, we need p-values. We need to know the significance values for these correlations to be able to build our correlation table. So there's another option. It's not as pretty as this, but it does give us all the information. And it's in the library called H miscellaneous. And so it's loading up that. Something I wanted to point out here, when this package was attached or loaded up, it says the following objects are masked if from the package deployer. So src and summarize with a Z, are no longer active because the H miscellaneous kind of took over there. Also, format pval and units were masked from package base. So it's letting us know when we upload or we load in a new package, if it has any kind of, what do you call, when you talk to the doctor because you're getting a new like antibiotic or something, and they tell you there's possibly an interaction with another drug you're taking. Like, so if there's an adverse interaction, if there's some place where this new package I just uploaded is going to be in conflict with a package that's already active, it gives me that information. That's all that's going on there. So I have the library started, and then this is the function rcore as a matrix on that. Remember just the continuous variables right there, and using a Pearson type of correlation. If I run that, let's stretch this out so we can see. So it's all the information. It's not quite as pretty, right? But here are the correlations among all of these. Openness to openness is a 1. Openness to conscientiousness is a positive 0.03, and so on. Here's the N, the sample size. So everything's 79 except for perceptions of research methods, that's 74. And then here's our p-values. All of these are p-values. So if I saw that I'm looking down this column because it's my outcome of perceptions of research methods is the outcome that we're interested in. And if I look down this column for the significant p-values, that one right there is the only one significant. The only variable significantly related to perceptions of research methods is conscientiousness. And knowing that, I can come back up here to the correlations and look at perceptions of research methods and conscientiousness and see what the R value, what the correlation coefficient is. It's negative 0.25. So, like I said, you have 3 tables to look at, but it has all the information you need for your correlation table. So then you would use that Excel starter table to help create your correlation table. You would get the information from each of those, your correlation table, indicate which ones are significant, and format it so that you can cross it into Word, which we did in the SPSS video, so I'm not going to repeat it here. So you can just watch that one. It's the same thing. Once we have the numbers, we just make our table whatever way is most convenient. Okay, now that we have described the variables and provided the reader with how are they related, how are the study variables correlated to each other, we're ready to move into model testing. And it starts with evaluating the assumptions related to regression. Mainly, at this beginning point, we're looking at univariate normality and bivariate linearity. And we assessed normality of continuous variables in a prior lab by visually inspecting the histograms and using the normality test, Shapiro-Wilks. So that's all we're doing here. We're looking at each of the study variables and asking for a histogram. Oops, it was confused by that because I selected part of it. So I hit escape because it was thinking that I wanted to give it more coding in the console, and I didn't. But getting out of that, hit escape, and it'll get you back to the prompt. So now I'll just put my cursor there and not select things and hit Control Enter. And now there's my histogram of openness. The Shapiro-Wilks says that openness is significantly violating normality because a assumption test, if you have a significant p-value, it means that it violated whatever it was testing. Now, to me, that doesn't look majorly violated. It looks pretty humpy look. So I would say visually that looks relatively normal, even though the Shapiro-Wilks test was significant. So you would do those same things for all of the study variables. And then you can go through and look at them and compare between what you're seeing. Like here's openness, and we already did openness. I'm going back in the plots to openness. There it is, and there's my p-value Shapiro-Wilks for it. For conscientiousness, it did not violate. So there's conscientiousness. Extroversion did violate Shapiro-Wilks. Agreeableness, very small p-value, violated the normality test, and so on. We just look at each one. You're going to report to your reader when you see a violation. And anything you feel like stands out from normal. If everything's all normal, you're not seeing a whole lot in the preliminary. You're just saying, I visually inspected the histograms and the normality tests and no violations were indicated. Something like that. Let the reader know that you checked them. All right, here on this last one, we have a warning message that removed 5 rows containing non-finite values. What's going on there is the missing values. So let's see if it'll take a NARM equals true. Let's see what that does. Okay, there's no warning there. So we already know that there are missing values in the outcome. And when there's missing values, sometimes that will work to get it to not give you the warning message. Even with the warning message, it still did the plot. So I'm not worried about it on that one. But when you see a warning like that, that might be an indicator that you need to put in the na.rm command telling how R should handle the missing values. Then, yeah, it wasn't impacting Shapiro's normality test. Like I said, if your visual inspection and the Shapiro-Wilks test are not in agreement, it's okay. Just let your reader know. So the next assumption we're going to check out is bivariate linearity. And this is saying that there is a linear relationship between the predictor and the outcome. And we have 2 predictors we're checking out. We're checking out conscientiousness and cognitive ability, because we're going to run them just as a bivariate regression first. 1 predictor, 1 outcome. And then the last regression, we're using both of them with the 1 outcome. So we need 2 scatter plots. We need one for conscientiousness with perceptions of research methods and another scatter plot with cognitive ability with perceptions of research methods. And this is using our ggplot. We're saying ggplot, I need a graph. I'm using this data set and I want a geom point, which is what a scatter plot is called. The aesthetics are that X is conscientiousness. Again, X is your predictor. Y is your outcome. And I went ahead and put NARM true there, since we know we have missing data in the outcome. Running that, we have a scatter plot. Looks like there might be a negative trend there, like we're evaluating visually the bivariate linearity. Does it seem like a linear trend is present? We can add a Lewis line, which is not the same as a fit line, but you'll see it takes that average for each X value, like the average of all the Y scores for 2 and the average for all the Y scores for 2.5. So here, let me run it. All I added was another plus and then geom smooth with the same aesthetics there. And now we have this line, again, not as easy to see as a fit line, but is there a negative trend there or not? What do you think? It is a subjective look at the graph and see what you think. Do you feel like that's a true linear trend, or it's pretty much no relationship? And then we can just copy what we already did. Once you write and then plug it in, but then change, now I want to look at cog ability total. And you can look at your names, cog ab total of your variables. Okay. And yeah, that looks all over the place. that does not look like a solid positive or negative trend. And if I want to put the lowest line, I add the plus, geom, smooth. Remember, capitalization matters in R. It won't work if you capitalize something that shouldn't be capitalized. I want cog ab total and y equals here m underscore time 2 underscore mean. So it's kind of just like that one, like the one with conscientiousness, but now with cogability. Yeah, that looks pretty flat to me. I don't think there's a whole lot of relationship there. But you report just that you looked at the scatter plot, report whatever linear trend you are perceiving, and the way and let your reader know. Testing, like the actual test of a bivariate linearity assumption, is the correlation test, which we already conducted earlier, and we just look at those relationships, the one between conscientiousness and perceptions of research methods, and the correlation between cognitive ability and perceptions of research methods. We can go to our core table there that we put the pretty one, right? And go across perceptions and see that conscientiousness was the -251 and cogability was 1.15. So, and if we need when we saw all in the output here, the p-values for those, the p-value for conscientiousness with perceptions is significant, and the p-value for cognitive abilities relationship with perceptions is not significant. So just let your reader know. And then as those assumptions are checked, now we're ready to run the linear model. And the bivariate linear model of perceptions predicted by conscientiousness would look like this. What are we saying here? I want the linear model, that's the function. Here's the arguments. It's the outcome, the dependent variable, predicted by that tilde thing over there beside the 1. Conscientiousness, that's the predictor. Comma, use the data, lab 2.1. So I let R know everything it needs to run that linear model function. So when we run this, this is the information we get in the console. It lets us know what we did, and it says the coefficients are 4.6883 for the intercept, that's the y-intercept. So when conscientiousness is 0, perceptions of research methods would be 4.6883. And then the regression coefficient, the unstandardized regression coefficient for conscientiousness would be -0.02696. So we need a fair amount more information to do the write-up, to fully interpret the model and the coefficients. So how do we go about getting those extra things? Well, whenever we want something done, and we're telling R we want it done, it needs to be something that's in the environment so that R can act upon that object. So we've run the regression, but it's just here in the console. We need to run it in a way where it becomes an item in the environment. And easy, just give it a name. I just made up a name for it, Percept1, because I know I'm running three regressions. This will be the first one. So percept1 is assigned by the linear model of the dependent variable, the little squiggle predicted by conscientiousness using this data. So I run that, and now it's in the environment as a new object. Now I can ask for a summary of that object. Like I couldn't ask for a summary of something that was not in the environment. But now that it's there, I can ask a summary. And now this is a lot more information that I'm going to need to convey to my reader. I have the model information. There's the F statistic was estimated at 4.66. There's the degrees of freedom for the F test and the p-value for the F test. All of that's about the model. The effect size of the model, the multiple R squared is the R squared. So that is my effect size, 0.061. And then the information I need about the coefficients, I have the intercept, I have its p-value, I have conscientiousness, the unstandardized regression coefficient for conscientiousness, and its p-value. But I'm still missing some information, right? This is a lot more information that I need for the write-up, but I still need more info. For the model, I still need the confidence interval for R squared. And for the coefficients, I still need the confidence interval for the coefficients, or the beta or standardized regression weight for an effect size, or something. I need more information there. So up here in model, to get the confidence interval for R squared, we need another package called MBIS. So I'll run that, or I'll load that up. It's already been installed. And the function and formula for requesting the confidence interval for R squared goes like this. There's the function. I need to give it the observed R squared value. I need to tell it the number of predictors, and I need to tell it the sample size. So here it is. The function, the R squared, I went ahead and put the whole thing in because why not? It's doing the math, not me. There's only one predictor here, conscientiousness, and the sample size was 74. Running that, we have a lower limit of 0 because that's as low as R squared goes. We have an upper limit of 0.199999 or 999518. So I'd round that to 0.20 likely. So I have my limits. I have my lower and my upper limit of the confidence interval for R squared. And I can put that in my write-up. Notice that this right here, this 0.025, probability at the 0.025 tail end of that curve, that normal curve distribution, and the probability at the 0.025 at the top. Well, if you take 0.025 and 0.025, it's 0.05. That's that 0.05 significance level. So it's saying you're 95% confidence interval with the little 0.25 on each end, the 95 in the middle. Okay. So that's the information we need for the model. The information we still need for the predictor, because we got the unstandardized regression weight and we got the p-value, but we still need the confidence interval and the beta, the standardized regression. To get the confidence interval, pretty easy, just ask for it. We already have the item in the object in the environment, so we run the function called confint, give me the confidence intervals for that object in the environment, and that object is the linear model. That's what we called it. So now we have the confidence interval around the intercept and the confidence interval around the predictor. Now to get beta, to get standardized regression coefficients, we're going to need another package. LM beta is the one that will get us that. And now we have to create another item in the environment. So we're going to run LM beta on the prior regression using, and this is just a new name I gave it. So it made sense to just go ahead and call it a beta, so I knew what I was looking for later when I look at things in the environment and I have all these objects there. So now I have precept 1 beta, and I can ask for a summary on it because it's now an object in the environment. So now we have the estimate, that's the unstandardized estimate. Here's the standardized estimate. So here's my beta for conscientiousness. And then the same p-values, all the information there. Notice that the F statistic stays the same. The multiple R squared is the same. The p-value is the same. It's just the standardized coefficient for that same regression. All right, that was a lot of information for just one regression. So let's try it like a little more streamlined without, explaining every step, because R really is fast once you are more comfortable with what you're looking for and you can just write the formulas. So we want perceptions predicted by cognitive ability, the other simple bivariate regression that we're running. So I want to say, let's say I call it precept 2. It's going to be assigned by the linear model of the outcome, so the dependent variable, PRM underscore time 2 mean, the little squiggly predicted by cog ab total, comma, then I need to tell it what is the data set. Data equaling lab 2.1. So I can run that. And now I have precept 2 in here. Let's get a summary now that I have it in the environment. So here we go with our model information and the cog-ab total coefficient information. But again, I still need my confidence interval stuff, right? I need the confident of precept 2. So the confidence intervals for the regression. I need the beta. So precept 2 beta. And that will be the function LM beta put onto precept 2. And then I can get a summary of that. And that gives me my standardized regression weight for cognitive ability. And I still need MBES, right? I still need the confidence interval for R squared. So I can just copy the one I did before and come down and paste it there. I know that it's going to be different, like it's still one predictor, it's still a sample size of 74, but it's a different R squared. It's 0.2376. 0.02376. Oh, I didn't type. 0.2376. Looks good. Alrighty. So now let's make sure we're getting from output to the write-up. Looking at this one, the second bivariate here. So when I reopen the lab sheet where we have the example write-up, looking at this one that we have the data for, linear regression was conducted to examine if we can predict students' perceptions of research methods based on their cognitive ability. We have a non-significant model, the F-test and degrees of freedom estimate. So here's the F statistic, and here's the degrees of freedom. Then we have the p-value, which is right there, 190. And we have the R squared, which is right on the line before it, 0.024, 0.0237, yep. And that's the one we turn into a percent. Cognitive ability was not a significant predictor. So cognitive ability, there's the estimate, the 0.039, which rounds to 0.04. The significance level says 0.19. Here it's 0.098. That's a difference between SPSS and R there, but they're both not significant. The beta, or the standardized regression weight, at 0.15. And then the confidence interval, which we had up here, we have, it does have a negative, no, but this is a regression weight. R squared is what does not have a negative confidence interval. This one's a regression weight, so it's different. So I have negative 020, here we have negative 0.198, it's the same thing. 0.98 and 0.982, that's the same thing. So making sure you can find the information here in the R output and get it into your write-up. How about this? Let's check that MBES. Did we do MBES? Yes, we did. So we have 0 to 135, and that's what we have here. Awesome. Alrighty. So our last regression is with two predictors. This is perceptions predicted by both conscientiousness and cognitive ability. So here's our linear model of our outcome predicted by conscientiousness plus cognitive ability total and where the data set is. So when we run that, we have now precept 3 and the coding needed to get the information for your model, the coefficients information, your confidence intervals, and your beta regression coefficient. So that is it for the RStudio portion of Lab 2, and I will see you guys in class.